Welcome to today's webinar. The topic from today's webinar is calculation of reinforced concrete slabs in RFM 6. My name is Alexander Meyerhofer. I'm responsible for the development and coordination of the reinforced concrete design in RFM 6. Today I will be your host of the webinar and answer your questions together with Juliane. My two colleagues can introduce themselves.
Yeah, hello, also from my side. My name is Adrian. I'm also part of the concrete team. And I will show you the presentation in the program today. Yeah.
Hello and welcome also from my side. My name is Juliane Stopper-Akta. I'm working in the Dubai support and I'm also supporting the developers of the add-ons concrete design and geotechnical analysis. And as Alexander said, I will be in the chat to answer your questions.
Okay, thank you. Please turn off your cameras so that the participants can see their entire screen. For those persons who take part the first time today, some organizational tips. On the right side of your screen, you can see the control panel, and with the red arrow, you can hide or open the control panel. And if you want to write a question to us, please enter the question here in this field and send it to us. If you want, if you will try, we will try to answer the question during the webinar. If there will be too many questions and we don't quite manage it, you will receive an email with the answer after the webinar. You can also watch the recording of the webinar afterwards and send us any question by email to the address info@dluboy.com. Now we come to the content, and for this I hand the screen to Adrian. One moment. So Adrian, it's your stage.
You should see my screen now.
Yes.
Yeah. So, oh, there's a German word left for today's content. I will start with the static structure based on the building model. So for determining internal forces before the design or before the calculation of the required reinforcement for ultimate limit state and divisibility. And then I will define an existing reinforcement and will adapt this existing reinforcement with the automatic design for the reinforcement. And then I will go to the design checks for UAS, for example, punching, and design checks for the divisibility, for example, the crack ride. And then at the end, I will show the calculation of the deflection in correct state, including creeping and shrinkage. And the last point will be an outlook about upcoming features in the program. So I will switch to RFM, to our today's structure. This structure of today's webinar refers a bit to an older RFM 5 webinar about reinforcing slabs and calculation or deflection calculation for slabs. This older webinar was a 2D position. Today I show or we show this based on a 3D structure. This 3D structure got 3 stories. The slabs are here in the right area, are cantilevered. I have applied some simple but typical loads, a dead load and some live loads here. And in the beginning, I will use the building model, so the add-on building model, to consider the slabs not in the 3D structure, but some kind like separated in a 2D structure. Before or in the beginning, I have to activate the building model add-on. You find it here. And at this point, I also will activate the concrete design, because this add-on we will need afterwards. And I agree. With activating the add-ons, the input or the possibility for the input in the navigator changes. And I have here an additional entry called building model. And I will start with the definition for the building model. So I first of all, I have to create building stories. I can do it. I can do this by hand, or I can use this automatic function that the program automatically recognizes the stories and generates them. This is this button here. And then I have to choose what I would like to, or how I would like to calculate with this building model. And there is one option regarding the floor modeling. And there I have to choose rigid diaphragm. This means that for the walls and the columns are connected via rigid diaphragm, and the slabs are considered as some kind of a 2D position, and for this, or as a 2D structure. It's not exactly a 2D structure, but it behaves like this. And for this slab, I have to choose how the attached walls and columns should be considered. So they are considered as nodal supports and line supports. But here there's an option how this should be done. So for the nodal supports, I can consider this the default option at the moment, consider them as fixed supports or fixed hinge supports. But I would like to consider them as elastic supports, or with spring constant, according to the member type which is attached. So the program recognizes which kind of column or which column is connected, and depending on the material and the cross section, the program calculates the stiffness. And this for the walls, it's the same. I can choose elastic wall, and then I have to choose how it is attached. So I will use hinge, so hinged in the bottom, at the bottom, and hinged at the top of the wall. So this is my input for the, let's say, 2D calculation of the slabs. And then I could start to calculate the internal forces. This would need let's say, half a minute or 1 minute. So I will save this time and switch over to a structure where I've already calculated the internal forces. And then you get results like, let's say, commonly for the statical analysis in RFEM, you get internal forces and deflections. But you have also an option, I can show it, where you could choose what kind of results you want to look at. So there are the common results from the 3D calculation, and there are the results for this, let's say, separated slabs. So this is these are the results which we use then for the concrete design. Yeah, I also will show another point. The program, as I mentioned, calculates the walls here, connected via a rigid diaphragm, and the floors, like, yeah, let's say separated 2D positions, and it also calculates some load transfer in based on a submodel which is calculated in the background. And here you could see, if I go to the navigator display and the surfaces, I can have here an option, loads from distributed surface. So now I see the loads as I defined them as surface load, but I can show them also how the program distributes the loads based on the submodel calculation. So I see how this surface load is distributed into the single parts of the structure. Yeah. So this is our, let's say, basic, or these are our basic results which we use for the concrete design. And now I will start with the concrete design, and in the first step, I would like to calculate the required reinforcement. I already activated the concrete design add-on. The input for the concrete design you could find in, like, I would say, 3 main areas. There's an entry here in the navigator, concrete design, and there are, for example, the configurations with all the settings for the design checks, and also there's here an entry for types for concrete design with input for the surface reinforcement, for example. And then there's also here in the table this point, concrete design, where you could choose which objects you would like to design, and also which loads or design situations you would like to use, and so on. So I will start, or I will do the concrete design for this slab in the middle here. So I show only this slab. I will turn off the results and take a look from the top side. Yeah, in the beginning, I will only design these 2 surfaces. So I will turn off the members and the nodes for punching or with punching, and I select here these 2 surfaces. And then I see here that they are at the moment not valid or deactivated, and the reason is that there is some input missing for the surfaces themselves. So this is the, let's say, 3rd area for the input. The objects I've selected here for the design, in these objects I have also a concrete related input. So this is here. It begins here with the register concrete cover, and then the following registers. So I can do here the input for the concrete cover. I could use it based on the standard automatically, or I could define it, or I could use it user defined. Then I have here the settings regarding reinforcement direction. So by default settings, the first reinforcement direction is always located in the local X direction of the surface. I keep here everything as it is. And then I go to surface reinforcement, and here I have to do an input. It is necessary to define a reinforcement or a surface reinforcement here. It is not necessary to do it absolutely accurate, but the program needs some diameter for the calculation, for example, and it also needs some input for the axis for the reinforcement, because these inputs are influencing the effective depth or the inner lever for the concrete calculation. So here I start with let's say some basic reinforcement. I define a mesh Q424 at the top bottom side for these two surfaces, and here I can see what the program then uses as an existing reinforcement. And I say OK or apply, both possible. And in the background, I see that the dialog is a bit. In the background, I see that the surface is switched from not valid to design. Yeah. So I will close the dialog. And here in the next register, design configurations, I have the related configurations for the design, so the ULS and SLS configuration. And then the last register is about the deflection. This part I will show later. So I will open the ultimate configuration and the visibility configuration. First, the ultimate configuration. Here I can do settings regarding the ULS design, for example, regarding minimum reinforcement, regarding shear capacity or shear checks, and so on. This is default. These settings are, let's say, related for slab design, so I keep everything as it is and close it. And then I will open the visibility configuration. It's quite similar. I have settings regarding the SLS design checks or for the SLS calculation. Here I would like to turn off the steel stress analysis because it's not necessary in each case. I also will adapt here the setting for the stress distribution for the effects due to restrain. So I will use bending restrain because I know I have here a slab, and the program has some automatism or automatic function to determine the stress distribution based on the load, but this is not necessary if you know what kind of restrain you would like to consider, and I know that I would like here to consider bending restrain, and at least I will deactivate the deflection analysis. This is an option I will use later. Then I have here this option which is activated by default settings, that the program increases the required reinforcement automatically also for the SLS, and here you have summarized for which design checks are used. So I keep this option on because this is my first step. I would like to calculate the required reinforcement. So now the input for is done, and I could start the calculation for the required reinforcement. And as mentioned, the program now calculates the required reinforcement for the ULS in the first step, and then for the SLS. And this is one way how you could work with the program. So this could be, let's say, a step how you handle your structures by calculating the required reinforcement. When it is calculated, you have here in the result navigator for the concrete design, you have here this point reinforcement, and then you could have a look at the required reinforcement at the top side in the first and the second direction, and at the bottom side also in the first and second direction. At this point, it would be theoretically possible to document the results, and then you have your concrete design. But you could do also a bit more, let's say, detailed calculation, and you could define the existing reinforcement a bit more detailed, especially if you later want to use the deflection calculation. It could be good to define the existing reinforcement more accurate, but also if you would like to do design checks for crack height and so on, or if you use this upper party design checks, these are done based on the existing reinforcement, and it is possible to define this existing reinforcement more detailed, and this I would like to show now. But first I would switch here from required reinforcement. There's also another option, not covered reinforcement, which shows the difference between the existing reinforcement, which is our between the provided reinforcement, which is the 4.24 square centimeter, and then I could use here this difference. So I see where this mesh, which I've chosen as basic reinforcement, does not cover the required reinforcement. So yeah, and based on this, I will do the an input for the existing reinforcement. But first, I would like to freeze these results because I would like to use them via input. There's an option here in the input data that I could say, if I change here something for the input, like the reinforcement, the program should not recalculate. It should keep the old results because I could use them via input. And then when the input is done, I could activate this again, and the program recalculates. So I turn this off, and then I will define the reinforcement, and I will start with the reinforcement above the supports. And I have to go to the navigator, and here's surface reinforcement. There's also our already our existing mesh basic reinforcement. I create a new surface reinforcement, and this time not for the whole surface. I would like to use a free rectangular reinforcement only at the top side, assigned to these two surfaces, and with diameter 20, and also here in the transverse or for the transverse reinforcement, also diameter 20. And then I would not do the input. I don't want a direct input of the rebar spacing. I would use the automatic function or the automatic design of the existing reinforcement. So if I click here auto, the program automatically determines the rebar spacing. So I have to give a minimum and a maximum value. I keep the default settings, and in increment I use a bit larger increment, 5 centimeter, and I do the same for the other direction and say OK. So now the program automatically determines the rebar spacing based on the required reinforcement. I will do the input. I have here the register direction and location. I will do the input based on a center and then side length for A and B. I took a look before about the size of the area. So it's about 2.5 meters. And then I click here on the middle of the support, say apply. And then yeah, it should show the reinforcement. I could also, to define the other reinforcement areas, I could here use the copy function. So it keeps uses exactly the same settings, and then I only have to change the location here. I can click apply, and again for the other one here, apply, and then it yeah, I have defined the other reinforcement areas very easy. There's also an alternative way. The surface reinforcement is like every other object in RFEM here. It behaves like a surface or something, or like a free load. I can select the surface reinforcement and use the copy function and say, for example, create a copy or create 2 copies, and then I could pick here my vector from start to end point and say OK, and then the program copies the reinforcement 2 times. Yeah, I have here in this area also some supports where also there is also some not covered reinforcement here in direction 2, and I guess in the upper corner there's also a small area here. I would also like to use this reinforcement for the support, so I copy it another time for this point and for this point and for this point, and say OK. So now I have defined for all areas where not covered reinforcement is above the support. I have defined this reinforcement here. It's not necessary to have for each reinforcement area 2 directions. So for example, here these 3 upper columns, there is the not covered reinforcement in direction 1, but not in direction 2. And also here, there is no required reinforcement or not covered reinforcement in direction 2. I would like to use this and show how you could adapt the reinforcement. So I could choose this 5 areas here, or this 5 reinforcements, and say I would not like, I don't want to use the second direction, and say OK. Here it is the same. I forgot this. Here it's the same. There's also not a not covered reinforcement in direction 2. And here it's for these 2s, it's vice versa. There is no reinforcement in direction 1, or the not covered reinforcement is 0 in direction 1, but in direction 2 there's some not covered reinforcement. So therefore I could also adapt these two. It's a little bit different. Here I have to switch off also the transverse reinforcement, but I have to say that the first direction is not in direction 1, it is in direction 2, and say okay. And then I have everything adapted as I would like. There is some reinforcement here in between these supports. So I will create another area at the top side here. I say new surface reinforcement, rectangular, choose these two surfaces, and this time I define the diameter and distance. I would like to use diameter 12 at 10 centimeter. Here also for the transverse reinforcement, and I have to check only at the top side. And this time I use this definition by corner points. So I have a grid in the background, so I could here choose every half a meter. This grid could be also adapted. I use the grid with half a meter, so I can define it here graphically like this, for example, and say okay. And then I have it looks a moment. I did some mistake here. It's always, you could always use the graphic to check if the input was correct. And then I have to define also two reinforcement areas for the bottom side. There's an area here where a not covered reinforcement occurs, and then also here in this area in direction 2 mainly. Also a small reinforcement in direction 1. So I define for these areas also an existing reinforcement. I could, this time I use the copy function again and copy my last reinforcement and switch to bottom. And then for the first one, I would like to use diameter 10 every 15 centimeter. And in this area, let's say from here to here, and say apply. I could check it, yeah. And then another area or another reinforcement at the bottom side here. And in first direction, I would use 10 at 30 centimeter, and in the second 10 at 10 centimeter, like this. And I use it for this whole area here, and say okay. And then I'm ready with my input. Yeah. So I could now start the calculation again, and with starting the calculation, the program will automatically adapt the reinforcement. So I go to the input data again, and I switch off this option. Say okay, the results are deleted. I could calculate again, and now I see that there's changed a little bit for the calculation. I have now two concrete entries. The first calculation is the required reinforcement. So with changing the reinforcement, there could be also changes regarding the inner ladder or the effective depth, depending on the defined reinforcement. And the second calculation is the automatic design of the existing reinforcement. So in this step, the program automatically decreases the rebar distance till this point that the required reinforcement is covered. There could be also the case that there is no solution, but then you should see the minimum distance. So in such case, you maybe have to adapt then the diameter, for example. So now the calculation is done, and I could have a look at the results. So maybe I start with the here, maybe at the top side with the not covered reinforcement. So now the not covered reinforcement is 0, and also in the second direction is 0. So in these areas where I used, or at this side where I used this automatic reinforcement, everything is covered. I could also have a look at now at the design checks, for example, at the ultimate limit state for the top side. Maybe I can, does not look that good. If I have this reinforcement turned on, I can switch it off here if I switch off types of concrete design. So I see here the design check for the UAS. Everything is below 1, so everything is fulfilled at the top side here, both directions. I could also have a look at the serviceability at the Crackwide design check, for example. I could here have a look at the ratio. The ratio is smaller than 1. For the top and bottom side, I could have a look at the directly at the Crackwide. So here I see the Crackwide in value in millimeter here. At the top side, the resulting Crackwide, and also at the bottom side. So this is this should show the possibilities I have here with this automatic reinforcement. And if I say, okay, the program determined this this distance, I can see it here, the value which was calculated. The program calculated this value, and I would like to use it as an input now. From now on, I could select all these. I could do it for each reinforcement separately by clicking here this arrows, but I could also select the whole all these reinforcement areas where I use this automatic function and say here with this function it should use the determined value for the rebar spacing in the input, and then I could say okay. And from now on, it does not need to recalculate the automatic function in the next calculation or for following calculations. So this is ready. The definition of the existing reinforcement is ready. Now, as a last step, I would like to do the deflection calculation and also the punching design. I will check at the beginning the input for the deflection calculation. There's I have to do it separately. One moment. There's an input here for this surface. Regarding the deflection, I could here select the surface type. This surface is double supported, and I have here a reference length 8.2 meter, which is the distance between the corner here at the edge and here the column here at the edge and the column here in the middle. And then I have this value also for this canter, for this balcony here, for this cantilevered area, and then I have surface type cantilever and reference length 2.65, which is the distance here. I also have to activate or check if the creeping and shrinkage is activated. So this is a setting or an option which I find in the material. It's a material-related property. So if I open the material here, I have an additional register, time-dependent properties of concrete. And here I could activate creep and shrinkage, which is used then for the deflection calculation. Here I also see the input for the creeping and shrinkage. This is regarding the calculation I showed today. This is for visuality. This creep coefficient diagram is for visualization, yeah, based on one thickness. So creeping and shrinkage is activated. The reference length for the limit value for the deflection is defined, and then I could check the serviceability configuration. I can now activate the limitation of deflection or the deflection analysis. Here I see the different limit values based on the type of the support of the surface, or yeah, if it is a cantilever or if it is both side supported surface. It uses different limit values, and then I will in this step also deactivate the determination of the longitudinal reinforcement, again because we have once now defined our existing reinforcement. I don't have to use this calculation again, so this saves a little bit calculation time. And I say okay. Of course, the results have to be deleted, but before I recalculate, I also would like to activate some nodes for the punching. So here, let's say these 3 nodes or 3 points at the columns should be used for punching. Punching design is also like surface design. You have the object with the input, which is for punching the node. If I click on the node, here you find that punching design is performed, and then you have a related ultimate configuration. I can have a look again at the ultimate configuration. And with selecting some nodes for the design here, I get this additional register for punching, and here you could find every single options for the design or how this punching load should be determined. There are a lot of different settings. I would keep everything as it is here. I would like to use the default settings, and then I recalculate again. But I use this calculation time and switch back, and will do a short explanation regarding the deflection calculation we use here for our concrete design. This is the deflection calculation according Eurocode 7.43 or chapter 7.43, and this is based on a distribution coefficient theta. And here's explained how the calculation would work without tension stiffening. This would mean the deflection is based on the consideration of a correct state. So the program calculates a stiffness for uncracked state, which is this function here, and cracked state. And so we have a stiffness for uncracked state and a stiffness for cracked, or let's say fully cracked state here. And depending on if the element cracks or not, it uses the uncracked or the cracked, the value for the uncracked or cracked stiffness. The stiffness itself depends on different parameters like existing reinforcement. This is also the reason why I did here some, let's say, more accurate input for the existing reinforcement. It depends also on the plate thickness, also on the height of the compression zone, material parameter, and of course also creeping and shrinkage. I have also the option to use the calculation including tension stiffening. This is our default setting, so if you do not change it, the program automatically always calculates the deflection, including considering the effect of tension stiffening. So this means there's not only the completely uncracked or completely cracked state, there's a state in between. So the deflection is calculated based on on effective stiffness. This means this distribution coefficient could not be only 0 or 1. It could have every value between 0 and 1. And based on this distribution coefficient, the stiffness is determined. So depending on this coefficient, and this coefficient is depending on the load and the height of the load. So we have a state between completely cracked and uncracked here. Yeah. So this is our default setting. The deflection calculation, by the way, and also the punching design are included in the RFM6 concrete design. So there's no separate or special add-on. It is part of the concrete design. So now the calculation is finished, and I have here for the design checks, I have an additional entry for the deflection calculation. So I could have a look at the ratio. Then yeah, I see the ratio for the deflection calculation, but I could also have a look at the deflection value itself. And here it says I have 4.6 centimeter deflection here, which would mean that the deflection would be not okay for this situation. It would be a bit too large. So there are different ways how to handle it. One possibility would be to increase the thickness of the slab. Maybe there's also an option to reduce some weight here in this area. Of course, there also the longitudinal reinforcement could be increased, or I would say I would consider a hock for the formwork here, so that I have a hock in the direction in the upper direction for the formwork to let's say cover this deflection. I also could have a look, or I could let's say compare the deflection a bit. Here I have the deflection for the concrete design. I could also have a look again at the uncracked, the value for the deflection for the uncracked state. If I switch back here to statical analysis, quasi-permanent load, and here I have the 9 millimeter, and then compared, I have the 46 millimeter, which is from the factor. It seems plausible. I could also have a look at the closer look at the deflection results in the design check. So if I, for example, use here, or if I take a look at this point here at the deflection calculation, I can have a look at the detailed calculation with all the intermediate values. So the whole program is not a black box. You see every calculation step here, also for the deflection calculation. I could have a look at, for example, let's say the calculation in uncracked state, in cracked state, all the stiffness values. If you would like to have a closer look, this is showing these design check details is possible for all design checks which are calculated in the program, not only for the deflection calculation, also for crack wide and so on, also the ULS calculation or the punching design and so on. Yeah, in the last point, I would like to have also a look at the punching design. So if I use the punching design here, I have also results on nodes where I could, for example, have a look at the required reinforcement for a node, like here, required reinforcement at the top side. The program with the default setting, it always tries to increase the longitudinal reinforcement to cover the punching. But I could also use then the existing longitudinal reinforcement, and if the existing reinforcement is not enough, the program will calculate required reinforcement for punching. Maybe this, to show, or to have a small look into the future and the upcoming features. One next step, which will be released in the program, will be the punching reinforcement. I have prepared here a small example how it will, or how it could look in the future. So if I have here, for example, a required reinforcement at one point, I could take a look at the required reinforcement at this node, and then I see how much how much reinforcement is required in which distance. I could also have a look at the details and, for example, see how high or what number of link legs I would need. So here, for example, it is 11, so to cover it, I probably need 12. And then I could define a punching reinforcement. So here, this is in the types for concrete design, there will be an additional point in the future, in the upcoming versions, with punching reinforcement, and I could create here new punching reinforcement. I keep here everything as it is, but I have to choose the node where the punching reinforcement should be applied to. And then I could use here the number of perimeters and number of legs in each perimeter. Here you see that there will also be an automatic function in the future. Now for this example, I will do it manually. So number of perimeters, let's say 3, and number of legs in the perimeter 12. And then the distance between the support face and 1 should be smaller, I guess, should be smaller than 0.107. So I would say 0.1 should work. And then the difference to the next is something about 11 centimeter. And then I say, okay, of course, it needs to recalculate. And then I see here the reinforcement. And I could recalculate the results. And now I see that the design ratio is fulfilled. So everything works here for the punching design with this defined punching reinforcement. Yeah, this should be just, let's say, small look into the future at the end. And with this point, I will hand over to Alexander, and he will give you an overview about upcoming features.
Thank you, Adrian, for the presentation. Before I will start with an overview of the coming features, I want to give some questions to you, which was asked during the webinar, and I think these questions would be also interesting for everyone. The first question was about the deflection calculation. Is it possible to consider the damage of the crack formation from a real design situation and calculate with the stiffness the deflection for the quasi-permanent loads? Maybe you can show it in the program.
I guess it's probably related to this option. So if you would like to calculate the cracked state, not from the quasi-permanent, but from the, let's say, real load situation, you could use now in RFM6, this is possible to have this cracked state detection here. So as default, the program normally calculates with the quasi-permanent load. It calculates the cracked state, and then it calculates the deflection. But it is also possible to calculate the cracked state from the envelope from all serviceability design situations. So like for the characteristic combination, the program checks in the beginning if an element cracks with the characteristic combination, and then it calculates the distribution coefficient theta based on this load, and then the load or the deflection itself is then calculated with the quasi-permanent load. So yeah, so to answer, this should be possible, yeah.
Okay, and one question more, what I would like to highlight is you designed now one slab in the building, and the question was how to define the surface reinforcement for the remaining slabs of the building. What is here the recommended approach?
Yeah, there are different possibilities. One easy way would be I turn on the reinforcement again. One possibility, it acts like with some kind of projection. So you could normally, if you would like to use the same reinforcement for the other slabs, you could select these slabs and just assign the reinforcement also to the other slabs, like here, like this. Okay. Of course, the results have to be deleted then. This is one. No, they don't have to be deleted. They have to be deleted when I choose also the surfaces for the design. So this is one possibility. Another possibility would be to copy all these surface reinforcement and then assign them to the other slabs. So in case you do not have exactly the same reinforcement, but some kind similar reinforcement, you could copy the reinforcement and then adapt it for the other slab. So this is possible and should be quite easy. Yeah.
Okay, super. Thank you for the explanation. I would like now to come to an overview of our current development projects and take the chance to give you an outlook to our upcoming new features for the reinforced concrete design. For this, I will take the monitor So I hope now the right monitor is shown to you. Yes. Okay, so the first feature which will come really soon is the definition of the punching reinforcement. It was already presented by Adrian, so I will go directly to our next feature. The automatically layout of the provided member reinforcement. With this feature, it will be possible to determine the number or the diameters of the rebars in a member automatically by the software. So generally, it will work in the same way like the today shown layout of the surface reinforcement, and it will be really a nice feature. The next feature which I want to present to you is a very big development in our company, the physically and geometrically nonlinear analysis of reinforced concrete. We have here really a completely new concept, and with this new concept, the calculation is directly implemented in the finite element calculation of RFEM. So it is possible to use the nonlinearity of the reinforced concrete together with other nonlinear materials, or for example other add-ons like the nonlinear pushover analyze and so on. This is one of the biggest improvements in comparison to RFEM 5, where the nonlinear reinforced calculation was an isolated calculation in the add-on RF concrete surfaces or RF concrete members for the participants who work already with RFEM 5. Further, it will be possible to define individual stress strain diagrams for the concrete or the reinforcement. So it is not only with fixed stress strain diagrams according to some standards. We can really work here with individual stress strain diagrams. The time-dependent material properties like creep and shrinkage will be available by two methods. On the one hand, with the modification of the Young's module, the so-called EEM method, which we used already in RFEM 5. And on the other hand, we will use so-called Kelvin-Maxwell chains together with the add-on time-dependent analysis. With this new development, it will be possible to consider in the add-on construction stages also the time-dependent material properties of the concrete. And in the new development of the nonlinear deformation calculation, it will be also possible to consider the tensile stiffening by the concrete tensile strength. For example, the method according to Quast, which was also in a question today in the chat. To summarize it, with this new development of the nonlinear reinforced concrete analyze, it will be really possible to design structures in the futures in RFEM 6, which was not possible in RFEM 5. So this will be really a big topic, and we are looking forward to release it in this year. The next topic in our development is the design of the shear walls and also of deep beams, which will be automatically calculated or generated, automatically generated in the add-on building model. Adrian showed already the building model, how it works with the load transfer. And with this building model, it will be also possible to generate automatically shear walls and deep beams as a design object. And these objects will be then directly designable in the add-on concrete. It will be a simplification for you. Further, our team is working on the seismic design according to the Eurocode 8. Last year, we already released the design of reinforced frames. It means the ductility, the constructive rules, and the capacity checks like strong column, weak beam are already available in RFEM 6. Now we are working on the required reinforcement for the rules of the capacity design. And parallel, we are working on the design of seismic voice and coupling beams. In the image on the right side, you can already see our first draft from the input of the diagonal elements or diagonal reinforcement in the coupling beam, which will then used in the seismic design. The next project, which will also released in 2024, is the fire design. For the fire design, we already released last year, at the end of last year, the design with the table approach, according to the chapter 5 from the Eurocode 2 for columns and beams. And the design checks for voice and slabs will be really released soon. It is in the final testing state. And currently we develop the fire design according to the zone method from Eurocode 2. And for this, we developed our own thermal analysis of sections. And you can see on the right side some isolines or the results of this thermal analysis, for example, after 90 minutes. Finally, I want to mention one of our high priority development projects, the new add-on concrete foundations. With this add-on, it will be possible to design single foundations. Currently, the geotechnical design checks according to Eurocode 7 are almost implemented, and we are working now on the calculation of the required reinforcement according to Eurocode 2 and also for the graphical user interface. This add-on will be also available or released this year for you. So as you can see, this year 2024 will be very exciting for the reinforced concrete design. We will release many things, and if you want to book a free online appointment, you can press here on this link on the right side, or scan here the QR code, and then you will come to our website and you can ask for an online appointment. I will go now to our website. So you will find today's webinar on our website www.luwal.com under news and events and webinars. If we go down, here you see the upcoming webinars, which will be the next weeks. For example, the connection with circular hollow sections in RFM6 or the design of masonry structures in RFM6. I think very interesting topics for you. And if we go down, we will find our today's webinar, the calculation of reinforced concrete slabs in RFM6. And if we go to the website, then you will find the recording, I think tomorrow here. And also the used structures and files will be here for downloading. When the recording is finished, you will receive automatically an email from us with the link to this page. So it is not necessary to remember it. You can use the link in the email and come directly to the webinar site. So this should be all from my side. I want to say thank you for your attention. I say thank you to Adrian for his nice presentation, and also thank you to Juliane for answering the questions. I wish you a nice afternoon. Stay healthy. Goodbye.
Thank you. Thank you for your attention. Bye.
Thank you. Bye-bye.